Hello everyone and welcome to my channel. Today, I bring you an exciting topic, Top 25 Junior QA Job Interview Questions, to equip you better for your journey into the world of quality assurance. While it might seem challenging, each interview question is a golden opportunity for you to showcase your skills and enthusiasm for the role. My goal with this video is to provide a roadmap that can guide you through your preparation in a manner that is focused and stress-free. So, without further ado, let's dive straight into these questions to tackle them like a pro. Before we start, let's dive into the fundamental question: what is testing? The International Software Testing Qualifications Board, ISTQB, describes testing as a comprehensive process covering all lifecycle activities and aimed at determining if software products adhere to specifications and are fit for purpose. The IEEE Standards Association views it as a process for evaluating a system based on its specification requirements. In contrast, Glenford J. Myers, an acclaimed author in software engineering and testing, sees testing as a process executed with the aim of finding errors. Moreover, Rex Black, renowned for his contributions to software and system engineering, expands on this definition, with a focus on finding defects, verifying functionality, and validating requirement compliance. While they express it differently, all these definitions place importance on the integral role of testing in software quality and efficiency, a crucial concept for every QA to grasp and perfect. So, based on definitions we've talked about before, testing is a thorough check of a software system or application. It's all about making sure the software works as it should, meeting both the stated requirements and the expectations of users, with no bugs or errors. We do this by running the software in a controlled setting, observing how it behaves and comparing these observations with our expectations. Testing is a crucial part of developing software that assures the quality, reliability, and proper functioning of the end product. So, let's move to the concept of the software testing life cycle, or SDLC. This is a series of structured steps that guide our testing activities throughout software development. Starting with test planning, we define our objectives, strategy, and scope. Test design then takes us into developing detailed test cases and scripts. We next set up an environment, simulating a real-world production setup in the test environment setup phase. Subsequently, we carry out the test execution, where we run tests and compare actual results with expected outcomes. If we find any defects during this stage, they're logged and tracked. In defect tracking and management, the team collaborates with developers to ensure identified defects are resolved. Test reports are then created in the test reporting stage, providing valuable information to stakeholders for decision-making. After any code changes, regression testing is performed to make sure existing features aren't affected. Finally, in the test closure phase, we summarize our activities, evaluate the process, and collect feedback for improvement. As you see, each stage of SDLC is a crucial part of the entire process, ensuring we deliver quality software. Now, let's turn to the question named the main development models and their principles. The waterfall model is a linear sequence of development phases, each completed before proceeding to the next, highly valuing clarity and rigidity. The V model, also sequential, forms a distinct V shape, emphasizing early defect detection and clarity at each stage. The Agile model emphasizes flexibility and continuous improvement, keeping the customer at the center of all development. The Iterative model leverages learnings from building earlier parts or versions of the system for continuous improvement. The Spiral model has 4 phases: planning, risk analysis, engineering, and evaluation, focusing primarily on risk mitigation during development. The incremental model involves developing an initial software product that is incrementally improved over time, simplifying debugging and testing. Lastly, the prototype model is employed when clients' requirements are unclear initially, starting with a basic prototype that is iteratively refined until the final product is developed. So, all these development models serve as guidelines to approach and manage software development efficiently and effectively. Moving forward, let's discuss the different levels in software testing. These levels are articulated in Mike Cohn's testing pyramid, representing how much testing should be conducted at different stages of the software. Unit testing sits at the base of the pyramid. These are quick, small tests, running frequently to verify the functionality of specific sections of code, typically managed by developers. One layer up, we have integration testing. This involves checking how different parts of the system interact with each other, mainly focusing on data communication between components. The third layer of this pyramid is system testing. System tests are run on the complete system, ensuring it works as expected as per the requirements. This includes both functional and non-functional aspects. Finally, at the top, we have end-to-end testing. This involves validating the entire workflow of the software under real-world scenarios, including interfaces with other systems and network connectivity. To wrap up, the testing pyramid strategy emphasizes running most tests at the unit testing level, gradually decreasing as we move up the pyramid. Adhering to this strategy assures most issues are identified and addressed early on, making the process more efficient and cost-effective. Shifting gears, let's explore two core testing strategies: positive testing and negative testing. Positive testing, often referred to as happy path testing, aims to confirm that the software works as expected with valid input conditions. Essentially, we're verifying that the software behaves correctly when it is used in the way it was intended. To illustrate, if an application field requires an email address, a positive test would check if it accepts appropriately formatted email addresses. On the flip side, we have negative testing or error path testing. This approach evaluates the resilience of the system when confronted with unexpected or incorrect inputs. The main idea here is to ensure the software can handle invalid conditions gracefully without leading to failures such as crashes. An example would be inputting an incorrect email format, expecting the system to provide an error message. In conclusion, positive testing checks that the system does what it should, while negative testing ensures it doesn't do what it shouldn't. These two testing methods combine to provide a comprehensive assessment of software reliability and user experience. Let's now distinguish between functional and non-functional testing. Functional testing relates to verifying that the software performs its expected functions. It is primarily concerned with whether the system meets the required specifications and focuses on fulfilling user requirements and expectations. Some examples include user acceptance testing, regression testing, black or white box testing, and integration testing. In contrast, non-functional testing pertains to aspects not related to specific user functions or requirements. Rather, it aims to refine the system's performance and usability. Its focus is on checking the system's readiness and ensuring it can withstand relevant demands. Performance testing, load testing, stress testing, usability testing, and security testing all fall under this category. Overall, while functional testing assures that the software behaves as expected, non-functional testing guarantees it meets performance and usability standards. Both types of testing work together to produce a reliable and user-friendly software product. Let's dive into two critical testing methods: black box testing and white box testing. Black box testing is focused on system functionality, treating the system as a black box, without any knowledge of internal workings. Testers interact only with the system's inputs and outputs, not knowing the underlying code or structures. It's primarily used to verify system behavior, detect incorrect functionalities, interface issues, or database access errors. This could include functional testing, non-functional testing, and regression testing. In contrast, white box testing, otherwise known as clear or glass box testing, delves into the software's internal structures or workings. As testers do know about the underlying code, they test the code, structures, loops, and conditions in the application. It can help uncover hidden errors, improve security, and verify the flow of the code, checking that conditions, loops, and statements function as expected. White box testing includes unit testing, integration testing, and system testing. Ultimately, a combination of both black box and white box testing contributes to thorough software testing, validating both the external functionalities and internal structures to ensure a reliable, robust application. Now, let's delineate between smoke testing and sanity testing. Smoke testing is intended to verify that the essential functionalities of an application operate correctly, particularly after a new build or significant changes. Executed in the early stages of the testing process, it assesses basic stability of the application. On the other hand, sanity testing is a concentrated examination of specific functionalities or modified aspects of the software. Its primary goal is to ascertain that these select areas function correctly and haven't negatively influenced existing features. Carried out later in the development cycle, it enhances confidence in the stability of recent changes. Both these tests, although different in scope and timing, play integral roles in bolstering the dependability of a software application. Next question I'd like to talk about is concepts of regression testing and retesting. Regression testing is a practice where we rerun previously conducted tests to confirm that code modifications, enhancements, or bug fixes haven't adversely impacted the existing software functionalities. The primary aim here is to prevent any new defects or undesirable side effects that may arise due to changes in the codebase. In comparison, retesting involves re-executing certain test cases that formerly identified defects. The intent of retesting is to ensure that all defects previously reported have been adequately fixed by the development team. Diving deeper into software testing methods, let's now discuss equivalence partitioning and boundary values testing. Equivalence partitioning is a strategy that reduces the number of test cases, dividing similar input data into groups. By focusing on one representative from each partition, we're assuming that if the software works for one value, it will work for all in that group. It ensures comprehensive coverage without the need to test every single input. For example, if the system accepts values between 1 and 10, we will use numbers -2 and 15 as an invalid values and 7 as a valid value. Conversely, boundary values testing focuses on the extremes or edges, cases, where input values lie on the boundaries. This is a frequently error-prone area, so testing this is crucial for improved error detection. Taking the example mentioned above, where the system accepts values between 1 and 10, to test lower border we will use 0 and 1. And for the upper border we will use numbers 10 and 11. These techniques enhance our testing effectiveness and efficiency, ensuring a well-rounded, rigorous evaluation of the software. Next, let's differentiate between load testing and stress testing. Load testing refers to performance testing, focusing on how a system responds under specific loads. The goal is to measure responses, throughput rates, and resource utilization under heavy load scenarios to confirm it can handle its intended user load without slowing down or crashing. In contrast, stress testing, also a performance test, pushes the system beyond its resource capacities intentionally. This aims at uncovering the system's breaking point, assessing its robustness, and observing how it recovers when pushed beyond its limits. Stress testing aids in identifying data corruption issues and the maximum load the system can bear. These testing methods help ensure that your software performs optimally under different load conditions and can recover successfully after stress events. Let's now discuss the difference between static testing and dynamic testing. Static testing is an early-stage testing method involving the review of the software's code, requirement documents, and design documents without executing the program. The primary focus here is the early detection and prevention of potential defects. This could involve reviews, walkthroughs, or inspections. On the other hand, dynamic testing implies testing the software or part of it by executing it and comparing the outputs to expected results. It validates the code during operation, verifying the software behaves as expected under varying scenarios and conditions. Dynamic testing can include both functional and non-functional testing types. Thus, both static and dynamic testing have distinct yet complementary roles in ensuring comprehensive software testing, from early-phase code reviews to real-time execution assessments. Let's now explore the unique software testing approach known as monkey testing. Monkey testing is an unconventional form of testing, performed randomly without predefined tests, aiming to stress the software and identify any crashes caused by unpredicted inputs. There are two main variations of monkey testing. First is dumb monkey testing, where random inputs are provided without any understanding of the software's functionalities. The objective is to cause the software to fail. Second is smart monkey testing. Here the tester has some knowledge of the software. They provide inputs that are thought to potentially crash the system, uncovering more sensitive and unusual bugs. In conclusion, monkey testing supplements formal testing approaches with unanticipated inputs and scenarios, enhancing software robustness and reliability under unpredictable circumstances. Going forward, let's differentiate between two key terms in software testing: defect and error. A defect, also known as a bug, is a flaw in the software that can cause unforeseen or incorrect behavior. Essentially, it's a deviation from the software's expected behavior or functionality specified in the requirements. Conversely, an error refers to a human-driven mistake made during the development process that results in a defect. These errors can occur at any development stage, including requirements gathering, design, coding, or even during testing. In conclusion, while a defect is a flaw within the software itself, an error is a human mistake that leads to a defect. Moving forward, let's discuss the concepts of verification and validation in the context of testing. Verification is a process through which we check if the system meets the specified requirements at the development stage's beginning. Essentially, it's about ensuring that we are building the system right. This examination phase doesn't involve actual testing, but focuses on compliance with the requirements and specifications. On the other hand, validation evaluates the system near or at the end of the development process to check whether it satisfies the specific requirements. Essentially, it checks if we are building the right system. Unlike verification, validation involves actual testing and attempts to demonstrate that the system operates as intended in real-world scenarios. In summary, while verification checks the system is designed and implemented correctly, validation confirms that the system meets the user's actual needs and requirements. Let's delve into the concepts of entry criteria and exit criteria in software testing. The entry criteria represent conditions that determine when to commence testing. They can include prerequisites like the availability of testable code, clear and complete requirements, test environment, and signed-off test plan and test cases. Unless the entry criteria are met, testing shouldn't start to avoid potential delays and rework. Meanwhile, the exit criteria establish when to conclude testing. They typically encompass conditions like the execution of all test cases, fixing and rechecking all severe defects, and reaching a certain threshold in requirements and code coverage. If the exit criteria are not met, then testing should continue unless further testing is no longer feasible or beneficial. In essence, these criteria provide a controlled approach to starting and completing testing, ensuring thoroughness and efficiency. Next slide answers the question about the concept of acceptance criteria in the realm of software testing. Acceptance criteria are the conditions, defined by product owners or other stakeholders, that a software product must satisfy to be accepted by a user or a customer. They set the minimum requirements for a function or feature to be considered complete and operating as expected. These criteria can encompass a range of aspects, such as specific functionalities that should be included, how the system responds to various inputs, the performance, adherence to standards or regulations, and compatibility with certain operating systems or devices. To put it simply, well-defined acceptance criteria provide a clear standard to measure the software against, reducing ambiguity and ensuring that the final product aligns with the user's and customers' needs and expectations. Let's explore the terms checklist and test case. A testing checklist is a document listing out conditions or items to be verified during the testing process. It's often utilized in exploratory testing, standards adherence, routine tasks, process compliance, and quick reviews. Essentially, it guides what needs to be checked or reviewed. A test case, conversely, is a comprehensive set of conditions or variables, including inputs, actions, and expected outcomes. Each case represents a specific test scenario, targeting to find defects or deviations from expected behavior. Test cases usually come into play in complex functionalities testing, automation, regression testing, and scenarios requiring preconditions. In essence, while a testing checklist keeps track of the items to be verified, a test case offers a detailed roadmap for testing a particular function of the software. Let's discuss the key elements typically incorporated in test case documentation, which lays out the conditions to evaluate the system's functioning. First, each test case needs a unique test case ID for reference and tracking. Second, a test case description provides a brief summary of what the test case intends to check. Third, precondition outlines specific conditions that need to be satisfied before executing the test case. Fourth, test steps provide a detailed, sequential guide of steps for the test, minimizing ambiguity. Fifth, test data indicates the input data to be used in the test. Sixth and seventh, expected and actual results outline the anticipated outcome if the system is working correctly, and the actual output after executing the test case. Eighth, post-condition describes the system state after executing the test case. Also, test case execution date records the date when the test was carried out. Lastly, status indicates whether the test passed or failed by comparing the expected and actual results. In conclusion, these elements help structure a comprehensive and effective test case document, thereby enhancing the testing process's robustness and transparency. When it comes to troubleshooting, a methodical approach is vital. So how to troubleshoot a failed test case? Firstly, analyzing the failure is a must. This includes reviewing the test case and understanding the scenario leading to the failing test. Next, review your test case to confirm its accuracy and check your test data for validity. Following this, try to reproduce the error. If the failure is consistently reproducible, it could hint at a genuine defect rather than a random or environment issue. If the cause is still elusive, debugging the test execution might be beneficial, as is checking code if you have the access and means to understand it. Reviewing logs can also provide crucial clues to the problem. Collaboration with team members is also recommended if you're still stumped, and they might bring a fresh perspective on the issue. If you confirm that the failure is due to a defect, report the bug in your tracking system with as much detail and evidence as possible. Finally, once the bug has been fixed, rerun the test case to verify the problem has been resolved. In essence, diagnosing a failed test case requires a blend of reviewing, replicating, checking, and sometimes, collaborating. Let's walk through the life cycle of a bug in software testing, which encompasses stages from its discovery to its ultimate resolution. Firstly, in the new or open stage, a bug is spotted by a tester during the testing phase, or possibly by other stakeholders like end users. Next, in the assigned stage, this bug is allocated to a developer or a responsible team member who will proceed to inspect and rectify the issue. Then, in the in-progress stage, the developer actively engages in fixing the bug. Once the developer believes the bug has been addressed and the code modifications have been implemented, the bug enters the fixed or resolved stage. Post this, in the verified or closed stage, testing affirms the bug has been successfully fixed and meets the specified resolution parameters. The bug is marked as such. Alternatively, there's a reopen stage, where a bug might be resumed if the issue persists or if new problems emerge due to the fix. In essence, the bug life cycle ensures a systematic tracking and handling of bugs from identification to resolution, maintaining accountability and efficiency. It is important to note that the bug status and their flow may vary depending on your bug tracking system and team processes. Now let's talk about bug reports elements. Creating a thorough bug report is crucial for reliable communication of issues identified during testing. Such a report usually comprises the following elements. First is a unique bug ID, or number for identifying the bug. Second, the title provides a concise summary of the bug. Third, the description gives a complete explanation of the bug and the situation leading to its occurrence. Fourth, steps to reproduce provide a sequential guide to recreate the bug for another tester or developer. Fifth and sixth, expected result and actual result document what the system should do and what it does, indicating the bug's presence. Seventh, severity assesses the bug's impact on the system's functionality. Eighth, priority suggests how rapidly the bug needs to be rectified based on its severity and the project's requirements. Attachments, consisting of screenshots, log files, video clips, or other relevant items, would be the ninth element. 10th, environment, details the specific hardware, software, and network settings where the bug was found. 11th, assigned to, indicates the developer or team assigned to fix the bug. 12th, bug status, describes the bug's current state. 13th and 14th, reported by and reported on, denote who reported the bug and when. 15th and 16th, fixed by and fixed on, signify who fixed the bug and when, if applicable. Finally, comments can provide any other essential information about the bug. To sum up, these elements collectively enable a comprehensive understanding of the bug, guiding its resolution effectively and efficiently. And like in case with bug flow, some elements might be missing or added, depending on your bug tracking system. Diving into the crucial aspects of software testing, let's delve into understanding the concept of a test summary report. A test summary report is a formal document that encapsulates the results of all testing activities of a specific testing cycle for a project or product. Its primary role is to present a clear snapshot of the testing activities and outcomes to stakeholders involved in the project. The key objectives of a test summary report include offering an overview of the testing efforts, summarizing the activities, methodologies, and duration of this phase. Outlining the results, covering the number of tests performed, their status, as well as the bugs discovered and rectified. Reporting the status of testing objectives, indicating whether these goals were met or not. Detailing any unresolved issues or bugs still needing attention. Highlighting potential risks concerning the product's quality or schedule. Providing any recommendations based on the results for future consideration. In conclusion, the test summary report serves as a potent communication tool, giving stakeholders vital insights into the efficiency and quality of the testing performed, aiding decision-making regarding product releases and further stages of development. When it comes to the testing process, traceability plays a critical role. Traceability refers to the capacity to connect and trace relationships between diverse elements of the software development process, encompassing requirements, design components, system components, and test artifacts. Firstly, traceability ensures complete coverage by linking each test case with its allied requirement, verifying that every requirement has been tested. Secondly, traceability simplifies impact analysis. It aids in understanding the impact of any changes in requirements on different components like design, code, and tests. Thirdly, it assists in tracing the origin of defects and offers insights into recurring problems caused by certain requirements or modules. Fourthly, traceability is crucial for verification and validation, ensuring that the finished product aligns with the given requirements and satisfies user needs. Fifthly, it boosts communication, maintaining transparency and clear communication among stakeholders like analysts, developers, testers, and management. Lastly, in many sectors, such as healthcare or aviation, documenting traceability between requirements, development artifacts, and testing artifacts is crucial for regulatory compliance. In essence, traceability enhances the efficacy, accountability, and compliance of the testing process, becoming an indispensable tool in software testing. As we delve into the final part of our presentation, let's discuss the benefits and challenges of automated testing. Starting with the benefits. Efficiency. Automated tests, operating unattended at any time, utilize resources more effectively, thereby curbing the time needed for testing. Consistency and accuracy. These tests perform identical actions every time, cutting down the risk of human errors that might occur in manual testing. Reusability. Test scripts are reusable across various development stages, providing cost-effectiveness in the long run. Improved coverage. Automated tests execute numerous complex test cases during a test run, ensuring coverage that manual tests can't. Faster feedback. Automated testing provides quick feedback to the development team to fix defects promptly. However, there are also challenges to consider. High initial costs. Automated testing demands a sizable initial investment for tools, setting up the environment, and scripting. Script maintenance. Test scripts require regular updates to align with changes in software features and functionality, leading to more significant maintenance efforts. Limitations in visual validation. Automation can't assess visual aspects of a UI like colors and font styles, which are usually verified manually. Learning curve. Each automation tool has a learning curve, and testers need appropriate training to use these tools well. Doesn't fully eliminate manual testing. Automation is excellent at detecting regressions and performing repeated tasks, but it can't replace testing that needs human intuition and experience. So, while automated testing carries several benefits, striking the right balance with manual testing, considering the challenges, delivers an optimized testing strategy. In this video, we've delved into numerous aspects central to software testing. We began by discussing key terms, such as defect and error, and proceeded to discuss critical processes like verification and validation. Furthermore, we explored testing conditions, distinguishing entry criteria and exit criteria, along with the importance of acceptance criteria. We've also touched upon test case documentation, discussing the fundamental elements. We analyzed how to troubleshoot a failed test case and trace the stages of a bug's life cycle. Importance was also given to components of bug reporting as well as the purpose and components of a test summary report. Finally, we discussed the significance of traceability in testing and weighed the benefits and challenges of automated testing. In conclusion, I hope this overview of software testing basics provides beneficial insights and contributes to understanding the complexities and critical aspects of this field. Good luck with your job interview. Thank you and see you next time.